Still a lot. What else can we do? All right, so the last thing that we can really look at, it's going to be tough to guess microseconds any better. There's too much lag between the server and us. The last thing left is 64 bits of this thing called LCG value. An LCG is a pseudo-random number generator, a PRNG, and they have it implemented in PHP directly. So LCGs have been around probably 20, 30 years now. They're well understood. They're also well known in how to kind of reverse LCGs. Now PHP uses a combined LCG where it actually takes two LCGs, XORs them together. So it's a little tough to guess how that works, but let's look at the code anyway. So we can see when the code starts off, with any random number generator or pseudo-random number generator, we want to seed the random number generator with some random value. That is what creates all the randomness from then on out. So let's take a look at the seed. So really quickly here, it does a get time of day. That basically returns the current time, both seconds and microseconds. And that's 32 bits of the entropy, called S1. So the 64-bit seed is split up into S1 and S2, 32 bits each. So we have basically our time of day, which is epoch XOR to the ones complement of the current microseconds. And then we have S2, which is the process ID. So let's look at S1 for a second. Now, microseconds is really hard to guess. But if we recall, microseconds only goes up to 1 million. That's only, let's see, that's only, well, basically we'll have the same 20 bits, right? 20 bits. So if 1 million is 20 bits, then what happens in a 32-bit value is we know that the other 12 bits will be static. So the really cool thing about this is we're taking the epoch, the time the person created their session, or I'm sorry, the time that, that PHP started, and we're taking the microseconds and XORing them together, basically kind of randomizing it. The problem with this is that we're taking the most variable value of the epoch, of basically how many seconds, minutes, hours, days, and we're XORing it with something we also don't know, the microseconds. But the things that we do know, like month and year, remain static. So if we actually calculate this, a little bit of math, and we can figure out that all we have to really guess is if we know within a 2-week period when PHP started up, all we have to guess is the other 20 bits. So we've reduced 12 bits from the total of 64 bits. So we still have 52 bits left to brute force, which is pretty tough out of the 64. Now let's look at S2, the other 32 bits of the seed. Again, this is the other half of the seed. Now the great thing about process IDs is normally on a Linux system, for example, it's only 15 bits. Only 15 bits for a process ID. So immediately we reduce 17 bits of entropy right there. So our 32 bits goes down to 15. So if we take our 15 plus our 20, we have 35 bits of entropy out of that original 64. Now the cool thing is, it's very easy to get a process ID. All you have to do, if you can execute PHP, you can run getMyPID. If you can execute any program as any user, you can run a PS, get that process ID. There are other ways to learn the process ID from web-based server info pages and PHP info pages. So all of this reduces that additional 15 bits that we didn't know. So now we have covered all of S2, all of that 32 bits, and we're left with the 20 bits of microseconds that we don't know. So this brings us down to 40 bits. So from 160 bits, we've gone down to 40 bits of entropy. You can brute force 40 bits. It takes a lot of time. It takes a reasonable amount of time, but we are talking about something I can do. But wait, there's more. We can actually take, the interesting thing about this is we can calculate those 20 bits, the microseconds from when PHP started, and the 20 bits, the microseconds from when Robert came on, and calculated them independently from each other. What that means is it's not 20 plus 20 anymore. You're not dealing with 40 bits. You're actually dealing with 21 bits. Because again, when you double something in bits, you're really just going up 1 bit. So we're technically dealing with 21 bits. With some code and a time memory trade-off that I've released code for, you can actually calculate that 120 bits within seconds on a MacBook Pro. So you're left with 20 bits. That's just over 1 million possible cookies. 1 million possible cookies. You can brute force that in a matter of hours in a day. On average, that means 500,000 cookies. 500,000 cookies, a couple of hours, and you have just determined someone's session ID on a website. So it's pretty scary. Pretty scary if you're using PHP in these cookies. So, how do we resolve this? How do we prevent this from happening? Someone attacking our website, either attacking our random values. For example, if you're using any sort of form software where you could, let's say, reset the administrator's link and you get a random URL string sent to the administrator, well, you now know what that random value is. You can actually reset the admin password because you guess what that link is. If people are logging in with sessions, you can now predict session IDs and log in as other people into the social network, into the bank, whatever you want to do. So how do you prevent this? Keep up to date. Make sure you keep up to date with software. I've obviously told PHP about this, and they've released updated versions that have cleared this up months ago. So make sure you're always on current releases. Keep up with security bulletins. Now, again, another thing, this is a difficult attack to execute, right? We had to communicate with the victim, and we had to learn his or her IP address. So there are some things that you have to pull off, but this is a very possible attack, and it can be done. It can be done today. So at this point, I have his session ID. I can actually log in as him. It's pretty cool and pretty scary. So at this point, what do? Well, I'll send her a message as Robert. So at this point, I want her to hit a URL. But because I'm Robert, she'll probably click it. It's her boyfriend. So let's start looking at what happens next. So this is your network. This is your network on drugs. Let's learn a little bit about NAT and networking, and we'll go back to web. So this is a NAT. So a NAT basically protects your computers somewhat. It's multifunctioning. So a NAT will typically take a public IP address and allow multiple systems behind that IP address to use that IP. It also has some other cool features. Just automatically, because it's doing this, it will block incoming traffic that's not destined to any specific computer, where before, if you have a public IP address on your system, you're going to, any traffic that comes to you or anything attacking a service is going to hit you. So NAT is a very easy way to block that immediately. It's kind of like an internet condom. So let's learn about something called cross-protocol scripting really quickly. Cross-protocol scripting is an interesting thing that gained some recent coverage. Basically, how you can use a web browser to communicate with a different protocol that the browser doesn't even know how to communicate in. For example, HTTP is a new line-based protocol. What that means is you're going, for every piece of data, you send a new line. You send an HTTP header and one value and then a new line, and another value and a new line. There are other protocols that are like this. For example, SMTP, our mail protocol. When you connect to a mail server, you say, hello server, and then it returns with a new line, a string and a new line. So there are other protocols that can communicate with new lines. Well, one of those protocols is IRC, Internet Relay Chat. So what we can do is we can actually use a web browser, write some JavaScript and HTML, and have that web browser communicate with an IRC server. So how do we do that? Well, first let's understand IRC a little bit more. When you connect to an IRC server, you just send these lines. For example, you say a line where you send user and your username, you'd send your nickname. Depending on the type of server, you'd have to respond to a ping request. You can then join a channel and you can send messages in that channel. So again, this is all new line based. So how would this work in HTML or JavaScript? How do we make that work? Well, the cool thing is we can create a form. In JavaScript or HTML, you create a form. You make sure it's a multi-part form data, which always occurs after your HTTP header. And we'll take a look at exactly what happens in a moment. You create this hidden form. You insert that username, nickname, all the stuff we want, and then we submit the form. Right? This is really the only JavaScript we need. So what happens? What does the web browser actually do if it sees this form? Well, first, it does its post request, all the normal things that the HTTP, that your browser is sending, and then it goes to your content, your post data, and it starts sending this. So what the IRC server sees is it says, you know what, I don't know what post means. I don't know what host means. I'm ignoring all these lines. Oh, user, I know that. I know that command. I know nick. I know join. I know private message. And now you've turned someone's computer into an IRC client that just goes online, goes onto an IRC server with their IP address, not yours, but their IP address, and communicates however you want as a malicious attacker. So that's kind of neat. So, you know, what can we do with that? Well, we can do NAT pinning. So what's NAT pinning? It's XPS times over 9,000. It's really cool. So NAT pinning not only confuses your browser, but it also confuses the router. Now, the router is pretty cool because the routers in these days are getting really smart. If you remember back in the day, you know, and you tried to FTP somewhere, a lot of the times FTP would fail, other protocols would fail, for example, multi-port protocols like FTP and SIP. Now, router manufacturers saw that and they thought, well, how do we make the router smarter? How do we make FTP work normally? Well, what we can do is we can monitor the traffic that's going on within the router. So now the router software is built to actually monitor traffic going through, specifically on specific ports, looking for certain commands and values. And it says, well, if I see one of these, maybe what I'll do is let's go on. I'll tell you. It's exciting, super exciting. So basically you have a malicious system that's supposed to say HP, my bad. You have the internet, you have your NAT, and you have a victim. Let's say PC1 is our victim. So what we do in this scenario is we send that victim a link. They go to this malicious website, and what I do is I make them connect to an IRC server again, like we talked about before with cross-protocol scripting, and I make them send a DCC chat. Well, what's a DCC chat? It's a direct connection. Basically with IRC, you can say, you know, I don't want you to chat me on the server because the server can see all of our communication. I want you to send me a direct connection so we can communicate directly and make sure, you know, no one's seeing this data. We can also have, we can do file transfers like this, and it will never go through the server. Now, the cool thing about DCCs is when you request a DCC, you don't connect to the person. You actually say, hey, I want you to connect back to me. I've opened up my port, and you can connect, and then we can communicate directly. Here's my IP address, and here's my port number. Well, this is really cool, because what if I say, if I'm the malicious server, and I set up a website, and I say, hey, connect to this IRC server, and then message this person and say, hey, I want you to connect back to me. This is my IP address, and this is my port 22. SSH, or let's say port 80, HTTP, port 443, HTTPS. The router will look at that. It will see within the IRC message, oh, my client, PC1, wants some remote person to connect back on port 22 so that they can establish this DCC session. Well, I better open up port 22 and forward it right to this PC, because they obviously requested that from the web page they hit, even though they have no idea any of this is going on. So with this code, again, you have a hidden form. You connect to that IRC server, which doesn't even have to be a real IRC server. It can be a connection that you have, a service that you have running on your side. It just listens to your data. The whole point is to get the router to see that you're sending this data on this port. It sends the DCC chat. Your router says, oh, I better send that back. Opens up that port back to you, the target, and now anyone on the internet can connect to you on any port that I opened, any port. So if you're behind your router and you think you're safe with your port 22s and port 25s and 80 and you're open, but you're only behind your NAT and no one can connect because you're not doing port forwarding and you're not doing DMZ, this will exploit that and get around it entirely. So what some browsers started doing is they started blocking specific ports when they heard about this cross-protocol scripting. So, for example, they started blocking 6667, the common IRC port. So, what can we do there? Well, what if we overflow the port? A port number is only 16 bits. So, if we add another 32 bits, or just another bit on top, and add 65536 to that number, we get some much bigger number. We get 72,203. The web browser checks, all right, is 72,203 equal to 6667? No, it's not. All right, great. I'll let this connection go through. But what's even cooler is that once it hits the TCP/IP stack, it has to get reduced to 16 bits. You just can't fit any more data in a source port. So it gets